All right, so we're going to start. Yeah, I see some of my students coming from the LP class. I tell them to settle. So this is going to be the last session, and this last session on the title is called Transportation in the Future. And we're going to run it a little bit differently than some of the other sessions, but let me give a little bit of a background on transportation. So if you think about transportation and the intersection with operation research, it's essentially as early as the military application. So if you think about some of the models that Danzig was interested in looking at, including problems that were dealing with uncertainty, they were essentially transportation problems. So moving people or things from places to places has always been a central part of the field of operation research. And of course, this is the operations research view as well. But there is a large portion of research that's been done in the transportation infrastructure, building roads, rail, airplane, in sensing and all that, that are not necessarily topics that people in OR or in business school would do, but people in engineering would definitely do. So I think the panel that we have here is going to try to represent a little bit of these various backgrounds. I didn't give them any specific questions to think about because I think they are all very, very smart people and they can answer questions on the fly. So we'll see. Right? and then I basically told them, well, we have 5, get 10 minutes talk each on research that you are passionate about and maybe linked to what the future of transportation can be. Being all faculty, they always talk more than 10 minutes, so I expect that it's going to be more like 15 each, but we'll see. But then we will then open a Q&A at the end. So refrain from questions at the beginning, and then hopefully there will be questions after that. And if you have no questions, have a long list of questions to ask our speakers. All right, so we're going to start in the order, in the alphabetical order here. So we're going to start with, so essentially what we're going to have is 2 faculty that they are all affiliated with the ORC, including David, that was a faculty at one point, so he's very much part of the home. 2 of these faculty also have an appointment in civil environmental engineering. One is Aeroastro, and David, what do you do? You are IE, OR, CS.
And CS.
Yeah. So we're going to have different perspectives. Transportation has been almost transformed again, and this is a very vital area of pursuit in terms of research on many dimensions. The engineering aspect of it, the computer science aspect of it, the OR aspect of it, and so we're going to have a different perspective from each one of our speakers. And we'll open the questions, okay? So Saurabh first. Saurabh is an assistant professor in civil environmental engineering, a background in control and optimization, and I will let him provide what his view is in transportation systems.
Okay, so great. So as Patrick said, my background is in control theory and systems theory. And what I have done in the past 6 years or so is to actually learn and draw upon a lot of tools from operations research and try to actually look for intersections between control theory and optimization, and more recently also game theory. And what I do in my research is to actually mainly worry about non-nominal situations in transportation, because transportation systems are in news, mostly for wrong reasons, in many situations for wrong reasons. So we have disruptions which are routinely affecting the transportation systems. You have, let's say, the long Thanksgiving weekend. You have multiple disruptions which are affecting the highway systems. You could also have perverse effects of information technologies, for example, Waze and Google Maps creating congestion, undesirable congestion in regions which we did not anticipate congestion before. And you have security failures as well as safety concerns thanks to the increasing evidence of autonomous systems trying to integrate with our highway systems. And this raises a concern not only of safety, but security in the terms of malicious actors trying to interface between the decision makers and trying to do bad things, right? So what do? We try to look for models, analysis and decision-making tools from optimization, from operations research community, and let's say if these kind of situations can be handled in different manners, okay? So that is actually the perspective which I'm going to try to provide in this brief time I have. So let me try to take a link level perspective. And here is where I want to draw connections from control theory and queuing theory. So consider that you have a highway link, which is an uncertain link, right? You have uncertain capacity of bad weather conditions. So you could use various kind of data technologies to kind of predict the incident or the probability of incident that can be happening. And suppose that there is some kind of a bottleneck of incident which one identifies, right? So what if one is able to kind of sense the presence of these incidents, both before and after, and operationalize the control loops in terms of regulating the inflow of traffic through these bottleneck zones in order to limit the impact of the incidents. So that's one situation. So the situation and the question here is how to design control strategies in the face of stochastic disruption. So Patrick didn't ask questions, so I'm going to pose additional questions throughout the talk, and there'll be many questions in this talk, right? So the similar situation could be in the context of a mixed traffic. Now, instead of incidents, we have connected and autonomous vehicle platoons which are trying to navigate to the highway, and these are creating congestion effects because of the stochasticity in the way in which they navigate through this particular system. So these connected and autonomous systems have the ability to interact between themselves and with the infrastructure. So what if we can actually try to take this information and try to actually do the regulation of the speed of these autonomous vehicle platoons so that the undesirable effects of congestion and throughput minimization or throughput loss resulting from this mixed traffic environment can be limited, right? So that is this question on how to model the traffic flow in this mixed traffic environment and to assess the impact of this heterogeneous traffic on the throughput and queuing effects. Now, on the security side, once we have sensing and control loops, one could imagine that malicious entities are able to compromise the integrity and the trustworthiness of this sense data, right? So what if somebody is able to create fake jams, right? And mislead the travelers and create congestion which is not anticipated otherwise? What if you have hacking of traffic signals where some external entity or a malicious entity takes control of the control loops and try to create both safety and security risk to the system? Right? So the question is how to improve the cyber-physical security in the face of strategic attacks. Right? So this is actually the broad link level questions which I want to pose, both from security and reliability perspective. And this goes to a more broader agenda of this resilience, which I view as a super attribute comprised of operational efficiency, robustness to random perturbations, and graceful degradation under malicious security attacks, right? So what I want to argue is that there is well-developed kind of modeling tools, analysis tools, and design tools which have been developed in queuing theory, starting from the seminal text of Larson and O'Doney, and then more recent papers which we found very useful in terms of fluid queuing models, in particular the paper of Batsimas, Gamarnik, and Tsitsiklis, and Dye and Main, and analogous developments in the transportation literature by Newell and Varaya, right? So the basic concept here is to draw from these queuing models and then try to actually integrate the models of disturbances, stochastic disturbances, incidents, as Markovian disturbances or more general kinds of disturbances, and to use the theory of stability analysis of Markov processes in order to understand the congestion effects, throughput loss effects in these perturbed systems, and then to try to design control tools in order to limit the impact of these disturbances. More recently with Patrick, we have been also interested in understanding what if the controller who is controlling this queuing system is misled because the information which is gathered by the controller about the state of the queue is false information. And this raises the question of how to optimally inspect the queues versus not, okay? So that is actually the link level question. Let me now move to two examples on the network level viewpoint, and then I'm going to try to summarize my viewpoint on the integration of link level and network level viewpoints. So in the network level viewpoints, in the context of reliability failures, we have this incidents that can happen, right? And in general, you could imagine that these incidents are actually sensed noisily, More generally, these are sensed by multiple information system providers, right, which may be not able to accurately sense the state of the system in an accurate manner. Right? So you have an environment which is a heterogeneous information environment where different subscribers of travelers, different travelers who are subscribed to different information systems are asymmetrically informed about the state of the system. So the question here is, how does heterogeneous information about traffic incidents affects the traveler's equilibrium behavior and route choices? And again, in the OR literature, there is a lot of work on congestion games, starting from the seminal paper on Price of Anarchy by Roughgarden and Tardosh, and there are seminal works here in the OR Center, in particular the paper by Correa, Schulz, and Stier Moses, and some very interesting economics work by Asimoglu and Ostagler. So the question here we try to address here is analysis of these congestion games by trying to draw on both techniques in congestion games as well as games of asymmetric information to understand what is the relative value of information, for example, the value of information faced by a Google Map subscriber relative to the value of information faced by an Apple Map subscriber, and more generally, how to kind of estimate the market penetration rate under this asymmetric information environment. So this, again, as I said, is a Bayesian environment where you have to have beliefs based on what the information you received, the belief on the state of the network, as well as the behavior of your travelers. And what you do is to actually understand how this belief influence your decision in this context of equilibrium route choice, and then to understand whether the value of information is positive, negative, or zero, and also estimate what would be the resulting change in the market penetration rate, for example, when an Apple Maps user tries to have new information acquired because of the technological advancements. Now, from a strategic viewpoint, and as Patrick mentioned, there's a lot of developments ranging back in 60s and 70s on the use of OR techniques in strategic environments, in environments where there's an adversary. But still, we find the need to kind of revisit some of these topics because now the adversaries are more sophisticated in terms of trying to interdict multiple links or multiple components simultaneously. So this is joint work with Patrick and Matthew here. And here we consider a stylized but fairly general model between the two players and draw inspiration from well-known literature, starting from Walmer, and more recently the papers by Morton and Wood, and Batsimas, Nasarabadi, and Stiller. But in our case, we try to understand the structural results in terms of what are the most critical components which an interdiction agency, let's say a surveillance agency who is trying to interdict malicious flow through a general transportation network, what would be a strategic way to kind of interdict these flows, right? So we provide these structural results, and in this analysis, we face new challenges in combining game theoretic ideas with combinatorial ideas and network flow problems, right? So it was a very interesting endeavor, a 2-year endeavor, which we just finished. Okay, so I'll try to actually provide a last perspective on how these things connect together. And here is where my thinking currently stands. So what we need is the right level of models, whether it is a network level model and a link level model, and to have disturbance models which are particularized to the questions at the corresponding layer, right? So at the network layer, we want to pose a question which is about dealing with random or adversarial disturbance who can target critical infrastructure components. And in the link layer, how to kind of learn the state of the system and how to utilize control techniques to kind of improve the performance of these queuing systems. Now, the open question which I want to pose, and I do not know how to solve, is how to connect these two layers, how to compose these models, how to have guarantees between these questions and the corresponding answers. Okay, thank you.
Thank you, Saurabh. We'll try to think about your questions and try to answer it in a couple of minutes.
We transition and then you do questions at the end?
Yeah, we're going to do that. So now we are going to have Amsa Balakrishnan. She's an associate professor, in aeronautic and astronautics, and she's also the associate department head. And one thing that I had forgotten to mention is that transportation is something of an interdisciplinary nature as well, and there is a program that is dealing with transportation, and I think you are in charge of the transportation at MIT. Is that correct? All right. Okay, go ahead.
Thank you, and I should say that transportation at MIT as a research initiative was something that Cindy
started in 2011, and I think there are several faculty in this room who have been involved, and I'm very recently have, because Cindy is really busy, have decided to help out with that. So Patrick said future of transportation, and I said I was going to talk about air transportation, and I think there's going to be a little bit of overlap between what I say and what Cindy says. So overall, since it's a broad transportation thing, I'd like to put in a plug for what I work on in the Aero-Astro department. Air transportation we really care about because when you think about global travel and commerce, it's something that affects a lot of people in this room certainly. About 5 billion trips a year are done by air, commercial air travel, and a little less than 50 million flights a year worldwide. Of course, with this demand, so demand worldwide is growing pretty steadily, about 6 to 7% a year. There are parts of the world where it's growing at in double digits, and so it's a challenge, and it's a challenge in a system which already is seeing the pain from the demand. So delays in the US cost somewhere between $30 and $40 billion. There's also a significant environmental impact and a pain point in terms of the amount of fossil fuel that delays consume. And so this is something that we care about, and we would like to improve the efficiency of the system so that we don't adversely affect the environment. So there's, in the future, what do we expect to see? Well, we're seeing things changing already to face these, some of these issues in terms of congestion that is cropping up. There are initiatives pretty much all around the world to look at next generation air transportation systems. And I'm going to talk a little bit about these trends and what it means for us in the OR community. So the kind of things that we would expect to see, and we do see, are increases in the levels of autonomy that we see in the aircraft and in automation as well. And the automation is something that I really want to emphasize, because we're not at a point where we're saying we're going to have complete autonomous air traffic control and we're going to take air traffic controllers out of the loop. But we're certainly at a point where we need decision support, and the only way we can come up with good decision support is through algorithms. And so that's one thing. And the second is going to be the manifestation of new sources of demand, and I'm going to talk a little bit about drones that I think a lot of you are familiar with, and urban air mobility, which is going to interact with things that Carolina and David will talk about as well. Ultimately, I think if we think about classic OR problems in the OR community, we've been very good at practical problems, and this is certainly a field where we need to combine the technologies, the cyber elements, and the fact that these are aircraft and the physical elements, but certainly the human operational elements in order to actually make a change. So there is a lot of history, as Patrick pointed out. Transportation is, has been embedded in OR. The first challenge is that there's limited capacity. And I actually want to start with this idea that the way to increase capacity is to build infrastructure. This is a paper which argues that we need a bigger airport. It sort of lays out how transportation planners historically would argue for a better airport using queuing models. And it ends with saying, fortunately, the taxpayers do not always believe the story. According to the planners of 10 years ago, there is no way O'Hare or JFK airports could operate today. And this is from a paper by Newell in Transportation Science in 1979. So this is a problem where, if you think about capacity, we've never had enough capacity in the system. And however, over time, we've realized that I'll show some impacts of the capacity shortage right now, but over time, we've also realized that you can't build a new airport. There are very few places in the world where the way to do it is to build a new airport and increase capacity. We really need to be able to use technology and use intelligent solutions to make better use of the capacity we already have in terms of the infrastructure. So one manifestation of this, of course, is what happens here. So about 20 to 25% of delays at major US airports currently occur when the weather is actually fine. So you're hitting the capacity constraint under good weather. But then the issue with air transportation is that the network effects are really strong because aircraft don't stay where they are, and so they end up getting system-wide very quickly. So this is, I'm going to just have data today. So the chart on the left is showing the number of, oh, sorry, how do I go back? Yeah, okay. It's showing the number of cancellations for each day by day of year over 2016. And historically, it's typically been things like, blizzards and big snowstorms, the kind of thing that happened this past weekend, which is going to shut an airport down and cause lots of cancellations. But the interdependencies are becoming much more apparent here. So in 2016, for example, in summer, 2 of the outages were because of power outages and computer outages in either an airport or an airline system. And when something like this happens, so this is, for example, the Delta power outage that happened in late August in 2016, and you see the impacts, and this is just showing within the US, but then you suddenly have worldwide a few thousand flights that are canceled because of a power outage at one airport. Just in terms of the scale of these things, the Southwest computer outage was 45 minutes long. The Delta power outage was caused by a fire in a router room and was about an hour long. The financial impacts to the airlines were $150 and $177 million. Because all of a sudden, you now have everything around the world that's scrambled, and then you have to get it back together, and it's an expensive proposition. What we can do and what we use data to do now is the ability to model impacts like this. And we really need to be able to understand these network effects and how things propagate in order to actually build the kind of tools that Saurabh talked about to recover from them. Because the other thing I would point out in this picture is the snowstorms you see coming to a large extent. And so you shut the airport down, you relocate everybody to the extent you can, and you can pick up the next day pretty well. On the other hand, the power outages and the computer outages now last a few days because you don't see it coming, and then the recovery from that is that much harder. So, and part of the reason is we don't fully understand how things propagate and where we need to put our resources in order to be able to recover from these systems. The third challenge goes back to the aspect that this is another sort of data point on this. As I mentioned earlier, historically, it used to be that the big snowstorms were the only things that would shut things down. So if you asked, how many days a year do I have more than 1,000 flights canceled? They would all be in winter, right? So snow was pretty much the only thing that would do. For the past couple of years, you have an increasing number where now pretty much we see a few every season, right? There's about, a few massive things. We've had 3 days already this past month. And of course, this is a winter effect, but we're going to have far more when it comes to next year as well that we're going to have to recover from. On the demand side, the autonomy piece is something that in all transportation systems we are seeing. I'm going to have a quiz here. So this is a headline, either real or fake, which says robot-piloted plane makes safe crossing of Atlantic. Right? The claim is that it was from Canada to England, fully autonomous. When do we think this happened? Or maybe it's fake. You can make fake news headlines easily these days. So this is from 1947, right? So for 70 years, we have known how to fly an aircraft autonomously. So it's not quite the engineering problem where can you make an autonomous aircraft? The remarkable thing I'll point out is this line from the New York Times article, which says we are going to have drone warfare and Amazon Prime, right? So, Amazon Prime, 70 years later, we have that, but it was pretty clear that the moment you were going to automate it, you were going to do this. Of course, what remains a challenge is integration. And again, that is an OR challenge because the engineering part is, the vehicle engineering part is, can I make one aircraft fly autonomously? And we've known how to do that for a long time now. We still don't know how to do this with a lot of aircraft interacting as well in mixed autonomy environments with human decision makers. And yet, when we think about the demand, that's really where it is. So part of it is, as I mentioned, there's about 6-7% increase in the demand for air travel on manned aircraft. But a lot of the new demand that's coming in is coming in from things like drones. It's coming in from urban air mobility, the idea being that Uber would like to have shared mobility, air taxi services in urban areas with aircraft, right? And so if you live in Sao Paulo or you live in the LA area or you live in Texas, this sounds pretty good. On the other hand, you already have a constrained airspace, and you have an increase in commercial space launches. And right now, you shut the airspace down every time you have a commercial space launch, which means you can't quite be doing everything without taking a serious hit in terms of delays. And so we do need to figure out how do we share this airspace. Again, these are scales of traffic that we haven't actually seen before. There are currently about 220,000 registered aircraft, right? This includes all the air carriers and all the general aviation aircraft in the US. DJI, the biggest Chinese drone manufacturer, currently sells about 250,000 drones a month, right? And it's growing. So we're now talking about a scale of traffic which is completely dwarfs the scale of manned traffic we've been talking about. And they want to access the same airspace where it's not all hobby flights which want to be really low down. They do want to access the same airspace as everybody else. And certainly when we talk about the urban air mobility, they're going to be in airspaces and in altitudes where you have to interact with everybody else. So with this, I've put together a set of problems. So I want to end with, what can OR do, or what are we going to spend, what can we spend our time trying to solve here. I do believe that the transformation can ultimately only be enabled by looking at data and looking at intelligence and looking at how we can leverage autonomy to do this. And I think there was a quote that Amadeo had yesterday from Ron Howard, where he said that models provide, good OR models provide insights. And I think we have now the challenge of having to do that in practice, where there's operational data, but we also need models and analysis techniques that can provide insights to all the different stakeholders who have, say and who have a role in the system. So everybody from the airlines to the the drone operators to the urban air mobility folks to air traffic controllers to the passengers. And I think that's where there are challenges. We need to be able to, there are still large-scale optimization problems that we need to solve. Again, air traffic flow management in terms of capacity allocation is a funny thing to talk about in this room with Amadeo and Dimitri's here, but I think we now have the combination of the technologies to actually actuate and to make, to carry out those trajectories that we would plan. So where we have the problems that we need to be able to solve, but at full scale. And we need to do this in a way that actually balances preferences of the aircraft operators or the airlines with what's good in terms of the system, because it's clear that this is an environment which has uncertainty, it has the human element, and it has competition, because everybody wants the same thing and everyone is competing for it. And so there's, again, now open questions in how do we design incentives and how do we design mechanisms. And ultimately, I think tying it to the problems in this session, I want to say that in transportation, in practice, what we want to allow for is enable people to get from door to door, right? You want to be able to move people and things from, doorstep to doorstep. We have now systems where the dependencies are not just within one transportation systems. They need to be multimodal. There needs to be a flow of information between these different systems. So there's, I think, challenges across the things that we talk about here as well. And then I will sort of end with the flip side of it when we don't do that very well, which is a few years ago, Atlanta had snowstorms in winter, and Atlanta has gotten a little bit used to bad winters now. And so the airport has bought snow removal equipment, which is unheard of, right? So the storm starts at 8 a.m., and they clear the airport out by 11, and so it looks great. Except Delta ends up having to cancel a few thousand flights that day, because it's okay if you clear out the runway, but if your crew can't get in and your pilots can't get in and your passengers can't get in, then there's no point having an airport that's working fine at full capacity if you can't get to the airport. And so really, when we think about resiliency and recovery, I think when we think about transportation systems, we have much more connectivity between all of these systems. So, there are a lot of open questions there. So thank you.
Great, thank you very much, Hamza. Our next speaker do not need an introduction, but I will do it. She's the Chancellor at MIT, Cindy Barnard. In addition to being very busy and successful doing that, she continues to do research. We had a students from the ORC recently, right? And
Yes,
so
I
that's
did.
great. Cindy?
Thank you. Hi, everyone. So let me make sure I can operate this. The big green arrow, I guess. Okay. So I won't wander too far from the mic, I guess. So I will have some repetition with Hamza that I will just skip over. I thought I'd begin by providing a little bit of context, and I thought I would focus on just a couple of challenges that I think exist. I'll begin by saying that in aviation, OR has been just a fundamental approach to addressing problems for decades, many decades. But then the message I want to give all of you out there is if you are interested in making a contribution, there's still tremendous opportunity in the airline and aviation worlds. So first of all, this is just a simulation of the US aviation system. It gives you a sense of the complexity of the system. And as Hamza already has pointed out, there is a lot of activity every day. The goal of the Federal Aviation Administration, first and foremost, is safety. And I'll say that they do an incredible job at that. After that, the goals are to use the resources of the system, aviation space, as well as airport capacity, et cetera, as effectively and efficiently as possible, and to provide access to airlines and to people to those resources in as equitable a manner as possible. Now, another key stakeholder of this system are the airlines. And with the airlines, again, they have a very long history of using OR techniques to, for example, in this case, schedule their operations and allocate their aircraft and their crews to their schedules. Their primary goal, one could argue, is to be profitable. So what I thought I would do is summarize in just a couple of slides what the state of the system is. First of all, I would say that despite the fact that we have used OR techniques for a long time and have, as a result, have significantly improved the capabilities of these systems, we still kind of have a mess. And I think Hamza made that point pretty well. Some might say that this is a delay-plagued system. As Hamza told us earlier, the costs are extraordinary. And what this shows is that half of the costs are borne by passengers because they're delayed and disrupted. And about a quarter of the costs are borne by the airlines because of all the delays, et cetera. They experience increased costs due to fuel, crew costs, et cetera. Okay, so what that means is the primary goal, I guess, of the airlines to be profitable has been a challenge, let's say. So if you look up from sort of 78 to 2008, the industry as a whole in the US was not profitable. Okay? So what I can say about this is that thank goodness we had OR, or it would have looked much worse than it did. Okay, so what I thought I would do is just take this little slice of the aviation system and focus on where I think there are opportunities for the future. So first of all, if what we're trying to do is reduce delays in this system and to help airlines be profitable so that the aviation system is sustainable, then we should probably first try to understand why there are these delays in the system. One major reason that there are delays in the US system is that there is a mismatch between the demand for capacity in the system and the availability of capacity. So in particular, if you look at airports in our system, you will see that there are many times throughout each day where the number of aircraft that want to use the capacity to land or to take off exceed the available capacity. And that exists for a couple of reasons. One is that capacity at airports changes. So as soon as you have snow, rain, fog, wind, the capacity can be reduced. The second thing is that we don't actually, at most of our airports in the US, we don't restrict the number of takeoffs and landings that are scheduled to match the capacity at the airport. We let the airlines schedule sort of at will, and then we ensure safe operations by limiting and matching demand to capacity. Okay? But that imposes lots of delays in the system. So two challenges that come immediately from this scenario is, one, we really want to try to figure out how to satisfy demand with the same sort of frequency of service, level of service, but reduce congestions and delays in the system. And as Hamza said, the solution of building bigger airports is not available to us. At least we'll assume that, because for the most part it's true. And the second challenge is, how do we help the airlines operate in a reliable and profitable way in this system? So I thought I would give you just a few examples of how we've done that. So first of all, the point of this slide is to say that increasingly I feel like as operations researchers, one of the ways that we can have a big impact is to think about how our models and algorithms can be used to affect policy. Okay? So in this case, the idea is, let's use the notion of schedule rationalization to try to reduce congestion in the national airspace. Okay, so the idea is this. At LaGuardia, why don't we do an experiment where we impose restrictions on how many flights can land and take off? And in fact, let's look at current operations and reduce it by 12.3%. Okay, so essentially that number comes from thinking about the number of flights that are scheduled and reducing that number to match the capacity in bad weather conditions. Okay? So a reduction of 12.3%. And then what we want to know is, if the FAA were to impose that at LaGuardia, what would be the impact? Now, to answer that question is sort of a paradise for OR people, because you have to figure out, if there's a reduction in capacity of 12.3%, what does each airline do? How do they change their schedules? What flights do they cancel? What flights do they introduce? And when do they schedule them? And that problem can be modeled, or the way we had modeled it, is to think about flight schedule design in a competitive environment. So what we did is we said, okay, we're going to reduce capacity at this airport by 12.3%. For every airline, we're going to figure out what their resulting schedule looks like. And then what we're going to do is we're going to take all the historical data that is so readily available when you work in aviation, and we're going to quantify, under that scenario, what would the delays look like to passengers, to flights, and what would be the profitability of the airline. And what you learn from doing that is that it's kind of a win-win-win, that by reducing the capacity, you're able to reduce delays to flights, reduce significantly delays to passengers, improve the profits of the airlines, and not decrease sort of the flight schedule service. Right? Now, what I think is important about this, and is kind of the broader takeaway for me, is that this could not have been done if each airline worked to optimize their operations. Because each airline acting independently has the incentive to increase their frequency to capture demand. So it's only through the FAA in this case imposing a policy limiting capacity that you would get to this result. And so to me, this is an opportunity for operations researchers to think about the problem from this policy perspective and system-wide perspective. Okay, so this is beeping, telling me that I did my 10 minutes, so Patrick's right, faculty talk too long. So let me try to do this one quickly. This is just another opportunity, and again, it's a specific example, but it's, I think, quite general and generic in its applicability. So the idea here is, in my mind, is as we think about how to reduce delays and improve service in a transportation system, sometimes we have to think about asking a different question. So for example, in this case, we have flight F1 coming into some location, sits on the ground for a little while, and then that aircraft flies out on flight F3, same with another aircraft coming in on F2 and out on F4. Okay, now every aircraft has a minimum time they have to spend on the ground to get everybody off and get everyone back on. And so what happens is if flight F1 is delayed, then the departure of F3, which is using the same plane, is also delayed, and so you have delay in your system. And this delay gets propagated downstream. Okay, so the thing is that if you instead say, well, I'm trying to assign my aircraft to flights to make sure every flight has an aircraft, but I want to minimize this propagation of delay, then you would probably end up building a different aircraft assignment or aircraft routing. And so what we did is we tested out this idea, again, using historical data, creating new aircraft routes and then testing what the impact would be. And what we found was that just by kind of reposing the question a bit, the propagated delay is reduced significantly by 44%. And the number of disrupted passengers, those are the passengers who miss their connections and end up being delayed often a long time, are reduced significantly as well. So again, I think that as we think about optimizing the system, we have to think not about optimizing the plan, but actually optimizing the realization, optimizing what happens when you operate the plan. And that's not always so obvious how you do it, but there's lots of opportunity, I think, to think about how to do that. Okay, so these are just a couple of examples of challenges that I think the industry is facing, and some examples of where, as OR people, we can have a big impact. And as I said at the beginning, although I gave you specific examples of things that have been done, there's so much more that can be done and needs to be done. So lots of opportunity there. Thanks.
Thank you, Cindy. Now we have Carolina, who is an assistant professor in civil environmental engineering and will provide another perspective on transportation systems.
Thanks, Patrick. Hi, everyone. I'm Carolina Osorio. And okay, so everything I do is urban transportation related, which facilitates things because we all have to commute and take our cars or bikes or the T on a daily basis. So I don't really have to describe the context as much as my colleagues here. So what I want to do is two things. One, tell you a little bit about the trends, which we all are aware of in urban transportation, and relate that to what I think are the key OR opportunities and challenges in that space. And then give you a flavor of how we in my research group have been addressing that with one specific problem. So in urban transportation, we all are aware of very high rises in connectivity. Think of vehicle-to-vehicle connectivity, vehicle-to-infrastructure. And so both at the level of travelers, of vehicles, of infrastructure, you know, we have plenty of sensors now and lots of really detailed data that we can collect. So on the one hand, that has one big implication when we think of transportation. So when I say transportation, it's always urban transportation. Just fill in that word. So one impact that has on the types of transportation models that we we need to develop is that now a local change, think of an incident like Saurabh was talking about on Memorial Drive, it can now have an instantaneous, very large-scale impact, okay? So your favorite traffic app will not just only update travel times on that, a specific link that has an incident, but also will update, route choice suggestions, departure time suggestions. And this could be affecting travelers that are, very far away for that affected link, right? Regional scale. So what that means is there is a trend and a need in the field to go towards larger scale models, actually accounting for how a specific mobility service is going to perform not just at the neighborhood city level, but even at the regional level. So that's a real challenge, especially if we're thinking of trying to optimize these systems. The scale of the spatial scale that we're trying to address is significantly higher than before. The second aspect of this is because of all this connectivity, demand and supply and their interaction are becoming more intricate, right? We're all actually checking constantly when we're commuting our phones and optimizing in real time, and you actually no longer need an OR degree to claim that you're a real-time optimizer of your travel decisions. All you need is, a smartphone. So that's great for us as travelers. It makes as OR model, it makes our life a little bit more tricky, right? Because what that means is we now have to have methodologies that account for how tens of thousands maybe of travelers are reacting in real time to the information they're being provided. And so it is shifting the field to a little bit more of a data-driven methodology versus the more traditional, I would say, analytical techniques. The other aspect of this, which I find really exciting, is the fact that I would say in the last 5+ years, there's been increasing presence of major private sector stakeholders. Up until, I would say, 5+ years ago, a lot of the innovations and the pace at which the mobility systems would evolve were really governed by the public sector. And as we heard yesterday in the public policy panel, the pace at which those types of sectors evolve and also the risk aversion levels are very different than in the private sector. And so that means that now in transportation, things are evolving at a much faster pace. That has a couple of implications. One implication is that if you ask me to forecast what mobility services are going to be successful in 5 years, it's making my job much more difficult. I would not make a bet on what services I think are going to be successful in 5 years. So now as an OR modeler, if you ask me what types of models or what should I be focused on modeling and learning better about, I don't really know. I don't know what is going to be the critical component in the system in 5+ years. So again, that talks to a need to more data-driven, flexible methodologies compared to what we had in the past. And also in transportation, our usual approach was to have a very detailed understanding of, for example, traveler behavior and of supply. And so we would, collect data over decades and have a very good understanding of how people make route choice decisions or how they drive. I think now we can no longer afford that, right? Because the mobility services are really changing, the way we're commuting are changing, so we don't have that time to actually develop the perfect model. And so today I hope to give you a few examples of how I think that as OR models, what types of problems we should be focusing on, not specific instances, but from a methodology perspective, how we should be thinking of what the role of data is and how that can be useful for different transportation systems. The main challenge I see in the field, or trend that I see in the field, is that decisions are really being made now more than ever based on very high-resolution data, high-resolution disaggregate description of demand and supply. But at the same time, we want to be able to solve regional-scale optimization problems, right? And so there's a trade-off between, if you look here at, increasing levels of detail, increasing levels of tractability, how useful they are or tractable they are for large-scale optimization. As you increase level of detail, of course, you end up with less tractable models. And so the dimension of the problems you can solve tends to be much smaller. So in transportation, we have names for these families of models, but you can think in OR, here you would have your math programming models, maybe analytical queuing models, and then increasing levels of details, you can think of simulation-based, sampling-based models, sampling from data. And so there's a lot of opportunities to end up here. Basically, how can we use our traditional OR techniques and couple them with more black box, complicated, data-driven techniques to actually be able to solve problems using a very detailed description of demand and supply, but also having our nice asymptotic convergence properties or nice problem-specific structural information that we can get from our analytical techniques. So I'll show you an example of how we do this in my group. And basically, the general question that a lot of our research looks at is, how can we directly use high-resolution mobility data and mobility models to enable solving very large-scale optimization problems? And so I'm going to give you a biased response to this question, and my bias is basically that everything I do, I'm very aware and committed and passionate about thinking about how can we actually solve problems that practitioners care about. So the projects are basically using a lot of data and partnership with both public and private sector stakeholders. So yes, everything is very OR driven, but there's always this underlying question of, can these methods actually solve the problem at hand versus maybe a much smaller problem that the stakeholder might not be as interested in solving or might not be as informative? So I'll give you one example of this. It's a problem called demand calibration. So basically it's a problem that in the public sector has been around for decades, and in the private sector, I would say there's an interest in the last 5+ years, mainly because a lot of major tech companies, what they're doing now is they're building their own in-house mobility models to be able to evaluate the performance of the mobility services they're provided. And so this problem basically says you partition your metropolitan region into a set of zones, typically in the order of, I would say, 1,000 zones or so. And you want to estimate for a given, let's say, Monday morning peak period, you want to estimate expected demand from every zone A, origin zone A, to destination zone B. So this is a continuous, it's often formulated as a continuous optimization problem. And if you're thinking of using the types of tools that practitioners use in terms of mobility simulators, you'd phrase it as a continuous simulation-based optimization problem. And so in transportation, what we've done typically is, take off-the-shelf algorithms that exist and use them for these types of problems. There's two main challenges to that. One is these algorithms, they're defined for very broad general classes or families of problems, not transportation specific. But at the same time, what that means is they treat these mobility models or these transportation problems as, black box problems. And so what that means is they're not really scalable or tractable. Problems in dimension of a couple hundred variables are considered to be, high dimensional currently in that field. And so in transportation, we're looking at problems that are orders of magnitude higher. And not only that, but on top of that, often the way we use them and the way practitioners use them is, you run your algorithm for a day, maybe a couple of days, that's it, you terminate it, you take the best solution you found so far. And these algorithms are not designed at all to have good, let's say, small sample or short-term performance. And so basically what we've been looking at is, if you go back to this, sorry about that. If you go back to this diagram, these would be the complicated, simulators that practitioners are using. And here the idea is, how can we use ideas from our traditional OR techniques, queuing models, math programming models, that have a lot of nice problem structure. They simplify the problem a lot, definitely a significant simplification, especially in how they describe demand, but also in how demand and supply interact. But they can provide a lot of problem-specific structural information, analytical information. So we design algorithms that try to couple both information from these more data-driven, disaggregate models, but also information from our traditional OR techniques. And the goal is, by doing that, you can end up with algorithms that have nice asymptotic, convergence properties, nice asymptotic guarantees, because you take general purpose simulation-based optimization algorithms that are designed for that. But then you embed information from problem-specific OR models. Think of, queuing models, analytical queuing models, math programming models, and that enables these algorithms to solve much higher dimensional problems, but also to become computationally efficient. So to come up with good solutions fast without having to run the algorithms for very large samples. So in this case of demand calibration, basically what we did is formulate a network model that uses a combination of queuing theory and traffic flow theory. So it's a super simplified approximation of what the transportation network looks like. It's basically specified as a system of nonlinear equations. If you have a network with n links, it would be n nonlinear equations, so it scales linearly with network size. So it's actually suitable for very large-scale, regional-scale problems, but at the same time, it's a significant simplification. And so if you go to any practitioner and you say, well, should I use this as a standalone traffic model to make forecasts or to use directly for optimization, I would not recommend that. But if you couple that with more detailed models that the practitioners trust and that are much more data-driven, well, in that case, you can end up with a pretty good recommendations because you actually have the data-driven aspect, the disaggregate description of demand and supply, but at the same time, the computational efficiency that is brought to us by our analytical techniques from queuing theory or from math programming. So we applied this. We've done case studies for Singapore. Some of you might recognize here a Singapore network. Here is the network of the metropolitan area of Berlin. And the main takeaways from there is, by combining these two families of tools, you can end up, first of all, solving problems that are orders of magnitude higher than what the general purpose algorithms can solve, because you're providing that analytical problem structure to the algorithms. And the second aspect, which is really important for practitioners, is you can actually solve the problems in a reasonable amount of time. So computational run times to come up with good solutions have been decreased by several orders of magnitude, which for practitioners is really, really critical. So that has led us to a variety of other problems in this area of demand estimation known as dynamic calibration problems. Also now with Kevin Zhang, who's in the audience, ORC PhD student, looking into real-time algorithms to try to solve these problems, not just in a matter of hours now, but actually in real time. And so we've extended this also to look into discrete problems. And there again, we've looked into formulations where you can take a general purpose discrete simulation-based optimization algorithm and embed from it information from your favorite math programming formulation, okay? And so you can show that by doing that, the actual algorithm can solve much higher dimensional problems, increases by orders of magnitude the dimension of the problems you can solve, but also, again, coming up with good solutions fast. So making these algorithms suitable for practice. And this was a lot of work based on work with Zipcar, where we started off, actually, Cindy was the one who introduced me to this first work. It was actually somewhat ironic because the proposal was to do car sharing, and we only ended up with bike sharing data, which now doesn't seem that crazy. At the time, we really didn't understand why Ford wanted to fund bike sharing works. And so we've continued that collaboration for a number of years, and now we're working with them on all of their major US markets, looking into different types of optimization problems that use really rich data from their reservation data, their search data, and then we couple that with math programming tools to actually solve some of their service design optimization problems. And so to wrap up, I think my takeaway, especially for the students in the room, is that if I think about what is the role of OR and what types of OR methodologies should we be developing for urban transportation problems of the future, I think the key is to no longer think of our OR tools as standalone tools. Okay? It's more about thinking about how can we couple these OR tools that have a lot, they're very simple, very simplified description of demand and supply, but have a lot of problem structure and have great properties when it comes to optimization. How can we think creatively about combining them with much more complicated, maybe data-driven simulation-based techniques, so that we end up with algorithms that still have nice convergence properties, asymptotic properties, but at the same time are relevant for transportation practice and can come up with good solutions in a reasonable amount of time.
Great. Thank you, Carolina. And now we're going to have our last speaker, David, who is from Cornell in OR, computer science, many things. Go ahead.
Thanks, and many thanks to the organizers for giving this opportunity to speak here. It certainly harkens back to the days that I was here. It's nice to feel included as part of the MIT family, and in particular, it gives me an opportunity to thank Tom Ignanti, who was a mentor for me during my years here and, of course, the years beyond. So I want to talk today about sort of my perspective on the space that Carolina referred to, in the sense that urban mobility options are being driven by the private sector in an interesting way, with many new opportunities and many new operational challenges. And it's exactly those operational challenges and the multimodality that's coming into play that I think gives lots more questions than we already have studied answers to. So let me just sort of start by giving you my perspective on how we got to where we are. And this is clearly a very personal perspective in terms of focusing on some elements rather than others. But I want to sort of start by thinking about bike sharing, which has its roots in France. The first really large-scale successful system was in Lyon in 2005, in Paris, which probably got the lion's share of the press, in 2007 with Vélib. It imploded a year ago, so that's why RIP. The first major North American adventure in this way was in New York City. It started in 2012 with City Bike, and there are a number of these sort of station-based bike sharing systems that are now an integral part of the urban landscape of mobility. The next kind of piece that layered on is, of course, the ride-sharing piece that emerged a few years later with Uber in 2009, Lyft in 2012. One personal note, put my Cornell hat on firmly here, that John Zimmer founded initially Zimride, which now, for those of you under 40, you won't get this, The traditional way in which people got transportation home for a holiday like Thanksgiving from Cornell was what we called a ride board. And this was not a virtual board. This was a literal physical bulletin board. And you tacked a little slip of paper and you said, I'm going home. I'm looking for people to share gas going from Cornell there. And Lyft had its roots in being an electronic platform that was ride sharing in this conventional way. Of course, it's quite a different object today. And this was internationalized. Didi, which was founded as two separate companies and merged a few later, is clearly a growing force in China as well. So that's the next piece. Beyond that, then there was the emergence of bike sharing in a dockless kind of mode. Again, there are many players in this space. In this case, the Chinese companies took the bull by the horns and did the most dramatic things in rapid scale. OFO and Mobike are perhaps the two most notable contributors. And then to this country being imported, I would give credit to Limebike for really propagating in a dramatic way starting in 2017. Now, if you look at China and what the issues of why maybe in North America there isn't, all I have to do is show you this mountain of discarded bikes to give you the sense of there are operational challenges in maintaining the fleet that are very different than when you don't have stations to organize things around. The next step, as I would view this ongoing revolution, is the pedal assist bike, the e-bike. The Social Bikes, which was founded in 2015, gave rise to Jump, which launched e-bikes in DC in 2017. And the station-based systems took this up. So Motivate, which operates Ford Go Bike in San Francisco and City Bike in New York, for its first major foray into e-bikes was in San Francisco in April of this year. And of course, Lime expanded into this way. I'm just curious, how many of you have ridden an e-bike, a pedal assist bike? So not so many. I urge you to try it. You'll discover that, I mean, if you want, for me, if I want to be able to ride at the pace of my athletic 20-year-old daughter, that's the solution. Another element to this piece is the scooter. And this isn't what the Italian scooter that you might have think of in the noir film of Diva. This is that kind of object. So it sort of looks like what I would describe as my kid's Razor scooter, but with juice, with a motor that can make you go at 15 miles an hour. And there have been a number of companies that have introduced these to both North American and international markets. Bird, Lime, Spin, all rapidly appearing on the scene really in this last year. And then there's this other element that you add on top of that. There's integration. I sort of called it vertical integration, but it's not vertical in the usual sense, but you might think about it in a hierarchical sense of sort of trunk transportation, last mile, last foot kinds of pieces. And Uber bought Jump. Lyft launched scooters and is in the process of buying Motivate. So these systems are having the possibility of integrating all of these different pieces, and this is happening as we speak, almost literally. So if I think about all these different components, it gives rise to new operational questions in actually running each of these different kinds of entities. So now I want to just take a step back and talk about sort of a little bit of my own personal work in this area. I've been leading a group at Cornell together with colleagues at Cornell, Shane Henderson principally, two PhD students, Daniel Freund and Owen Omany, and a host of other students at all various levels, including several of you who are PhD students at the ORC currently. So, bike sharing in the station-based thing, you open your app and see what stations there are, what the availability of bikes are, what the availability of docks are, and a user can go either use the app or a personal key, release a bike, and rent it at one station and return it at another. And that gives rise to the key challenge of operating a bike sharing system is imbalance, that you have directional flows of bikes from one part of a city to another, and you can see in one part of the city stations completely empty, in another part of the city stations completely full. And of course, your idea is how to mitigate these imbalances. And City Bike and Motivate more generally has a number of levers that it can use. It can use vehicles, a van, to actually physically move bikes around. That's kind of tricky in rush hour traffic, so you can use these trailers that are sort of overgrown pedicabs that can transport bikes that can weave next to traffic. You can give surge capacity by having these corrals, and we'll talk about an incentive system in a second. So, if you think about why is rebalancing complicated, in some sense you have two-sided stockouts. You can have the same entity where you can have either stocking out of docks or you can have stocking out of bikes. You have this dynamic system where independent entities are moving the capacity around. You don't have perfect knowledge of data. You have stockouts that are censored. And of course you have underlying routing problems that are going in terms of trying to mitigate the outages that you see. So one thing that, as I started working on it, I was always confronted with the question that if you think about it from a system of sustainability, is it really helping? And I have to say, it always gave me pause. Because if I think about the balance between what the motorized rebalancing was doing versus the amount of transportation savings of replacing other forms of transit with bikes, it's not clear what the answer was. But so one question is, can you achieve rebalancing in a purely non-motorized way? The valets that I meant, the surge capacity is certainly one way. But perhaps the most effective thing that we introduced is a crowdsourced view to rebalancing. And I'll say a little bit more about that. It was marketed under the name of Bike Angels for that, and you get quotes on the website currently like, I like to do a Bike Angels workout, where I'll bike north in Central Park to an empty station, then run back down the park and repeat a few times. And you can reallocate docks to part of the system. Now, I'm only giving you a whirlwind flavor of this. My other home, in addition to the ORC, when I was on the faculty, was applied math, and I'll actually be giving the applied math colloquium in 2 weeks, and I'll give a much more detailed version of the research underneath this. So when push comes to shove, we can reallocate docks. This is a snapshot of if I were to reallocate a few docks, or if I reallocate more docks, you get a sense of what the trends are. One bottom line might be is move docks from Manhattan to Brooklyn, which makes Brooklyn mad, almost as much as not plowing. But the biggest invention that I meant was this incentive system. In many ways, sort of the original sin in bike sharing systems was the pricing mechanism, which is basically driven by an all-you-can-eat subscriber model. And the question is, how do we actually introduce an alternative form of currency so as to incentivize users to do good rides? And this is what this Bike Angels was about. Here you see a schema of a map of where we're incentivizing users to bring bikes and where we're incentivizing users to take bikes away. There was a point system that we could do. And one of the things we threw on just, it made sense, it was in the air, let's gamify. Let's think about maintaining a leaderboard of who's got the most points. And that will encourage users in a tangible way to do this. Little did we know what we were breeding. So here, and you get prizes for accumulating points. Here's a GIF that shows one user who got obsessed. This is Joe, and this is April. And you'll see, these are the rides that he made in the month of April, accumulating points. And you remember those points were at the 1 or 2 per level over the month of April. And we're getting there, and lo and behold, he'll get up to essentially 9,000 points that he accumulates doing good of bringing bikes where we need really for pennies. And so this gives a much cheaper way for rebalancing the system in a purely sustainable kind of way. So that gives a flavor of Bike Angels. It's been not only in City Bike, it's been exported to other Motivate systems, even in Montreal, where it's rebranded as Les Amis Big C. And that gives you a sense of the operational problems. Now I'm way over time. I don't know if I'm over time yet, but I will be, so I'll go quickly. So that was bike sharing. Ride sharing. So if you think about what's driving Uber and Lyft, if you think about what happens with dispatching cars to users, in some sense, classic, where you're just one person, one car, that's easy. That's, well, relatively easy. That's online stochastic bipartite matching. We all know that. We have good algorithms. We understand that well. Pool, where you actually share a ride in ride sharing with other users, all of a sudden, that becomes much harder. Now things get even harder because There are services that called like Express Pool that Uber has that tell you to suggest places that you might walk to so as to decrease your cost further. This gives rise to even harder optimization problems. Now, in addition, you want to have scheduled rides where you book in advance, or services that you've all seen on your app that you get swapped to a new car, how you actually integrate that into model. And you see there's this complex layer of hierarchy of new, interesting optimization problems that are absolutely wonderful grist for our algorithmic mills. And of course, these are all problems that are at scale and have to be solved more or less in real time. If you think about scooters and e-bikes, there are new questions on top of that. There are charging stations. These have things that have power. Do you charge by actually docking into a station? Do you swap out batteries? Do you crowdsource that and send them home with a juicer to charge at home overnight? Scooters, for whatever reason, basically get collected overnight. So then every morning you have a daily distribution problem of how you actually lay out a particular pattern to where the footprint is going to get used. And of course you have an end of day collection problem, all good OR problems. And of course there are different usage patterns for every type of vehicle. And if I have to say, or I bet that what the e-bike is going to do, I wouldn't bet on grown-ups, at least, aside from purely athletic pursuits, using the conventional bike. The e-bike is going to really, especially in a shared mechanism, is going to revolutionize how people use bikes. And the other question throughout this is, how do you price? So, I mean, there are operational problems of making sure the supply is where you want it to be, but pricing is going to be key. Now, I would maintain that all of these sort of individual questions with respect to a different kind of vehicle are somehow the easy questions. What's really the big challenge is sort of the multimodality of it. How do we make these different kinds of modes of transportation mesh together and with the normal, traditional public infrastructure to really build an effective system? How do you actually even measure performance? What is good performance from an operator's point of view? If you think about that distribution question for the scooters every morning, one way to think about it is you have multiple firms competing for the same landscape. Then all of a sudden you have a repeated game in a multiplayer kind of way of trying to control territory and trying to get results in terms of how their service is being used. And to a large extent, all of these firms have separated to a substantial way pricing from operations, and the integration of them also proposes interesting new challenges. But one question that another kind of flavor that you need is, from a design point of view, we're clueless. I mean, if I station-based or literal virtual station-based kinds of sharing opportunities from an operational point of view, I believe are going to be here to stay. And if I wanted to install a range of services in a city, and I wanted to know what was the right way to thinking about setting that and interfacing with the existing infrastructure, which is much more static, what's the right way? How do I think about that? What's the right footprint? All of these kinds of questions are fundamental modeling questions where almost literally, not quite, I don't know where to begin. And of course, on top of that, there's the elephant in the room that I haven't talked about that, and that's the autonomous vehicle. I was thinking maybe primarily on the ground. Of course, clearly there's the autonomous vehicle in the air. And these are all interesting questions of how these systems are going to interplay. And with that, thank you very much.
Thank you very much, David. Yeah, so as you can see, people are always very, very excited about the research, right? So you had like 5 presentations of excitement. I counted about 4 dissertation topics per topics. So 4 times 5, 20 dissertation topics. So that's good. Right, exactly. Okay, so let's open to question and answers. Dimitri?
So, this is an area I know very well, David. But, I mean, I have used Uber and Lyft multiple times, and I have observed the cost is roughly half of a taxi ride, approximately. At the same time, when I look at the finances of these companies, they bleed money. That is, the VC community has pushed billions of dollars per year. Clearly, that's not sustainable. I mean, obviously, they are preparing for an IPO and so forth. But independent of this, at some point, the money has to match. In other words, do you believe I mean, and I share with you the excitement of the OR problems as well, but as an issue of society, do you see this in a sustainable way? You are in a good position to answer.
I hope.
Especially for the finance sector.
So you're quite right to raise the question, and I think the topmost answer is I hope so, but it is a hope, not a belief, in the sense that it is a real question. And I think that the future is really going to be in understanding those really shared rides. So the sense of, I mean, if for other than starting at an airport and delivering people, the number of times that the number of passengers in a car is more than one is a very small fraction of the time if you for either company. And the challenge is how to do the optimization. And it is really a question of doing the spatiotemporal optimization that's underway in a way that really makes these services effective. And it's clear that we just don't even begin to understand it. I think that, I mean, both companies have played with more scheduled kinds of services or more van kind of services so as to change the mix of their, and this is all going to come as we understand how to optimize and how do we build trunk lines. Their buyouts of the more flexible mobility, the scooters, are all about trying to help build a hierarchy so as to improve quality of service and trying to think of building collection points, right? So if I can do a better dispersal of these low-cost vehicles of scooters and bikes, and I can use that to link up with a ride which is going to take me the trunk part, or take me to the public transit part. And it's also the integration with public transit is a huge challenge and I think going to be key. So I think we're just scratching the surface in trying to understand how to make these pieces go. And they're buying people's goodwill in the meantime as they sort of build the plane in midair.
Maybe I can add one more thing to that. I think in the long run, they have a major role to play when it comes to first mile, last mile problems. So connecting you to a more traditional form of transportation. And there, I think they can keep the prices that they're currently at, or maybe a little higher, but definitely not, significantly higher. I think when it comes to full trips, I think there the pricing mechanism would have to significantly change for it to be actually financially viable.
Other question?
Digital sky policy. The no permission, no takeoff with firmware on every drone. How do you think that's going to work?
So I think there are two issues. One is I think it's users technology. So I think you need some sort of permission. You can't to do it. I don't think all the solutions can be regulation based. So I think that's the challenge here, which is we've always historically managed airspace by strong regulation and then just saying you can't fly, which is sort of how we try to do the US airspace. That stifles innovation. I think it's pretty clear. So when you want to have transformation at some level, you can still need to say you can't fly without permission, but you need to be able to then face handle the demand that's going to come in for people filing flight plans. But it's a step forward where at least they're not saying it's a ban. So, yeah, so, I'll take that as a positive step.
And unique identification, has become a big...
And I think, some of the security issues that Saurabh raised are also here because with off-the-shelf software, you don't have the certification that you have on commercial aircraft on these drones anymore. So,
I think they've convinced the Chinese manufacturers to actually put the firmware on, but that's just the first step.
Yeah, right.
So how do you think the vision of autonomous cars will disrupt the current models? You can imagine even with that space, models in which all the infrastructure is being owned by the operator, which is something that currently Uber and Lyft do not do, but even scenarios in which, I have my own autonomous car, but instead of driving and doing service for Uber, I just lend my car to Uber or to the operator, it seems that it's going to have quite a dramatic impact on not only the business model, but the kind of optimization models that you want to solve. And I don't know if you have any thoughts about that.
I mean, so clearly, I mean, if you think about it from a Uber Lyft kind of view, they have currently decentralized control, right? In terms of they can tell drivers where they should position. And yes, they can use pricing levers to do this, but once you have a body of autonomous vehicles, you can pre-position, and that will help serve to smooth the curve, whether it will justify what will be a pretty substantial cost for autonomous vehicles. That may be, I mean, so I wouldn't want to bet whether autonomous vehicles are going to be largely in the private domain in terms of just a small segment of society that's going to shell out the money. And yes, you know, maybe there'll be the sort of mixed mode that it can be used while they're not using them by others. I could also imagine a setting where we go back to a more truly shared economy, in that people buy shares of autonomous vehicles just without engaging with it being used in a public way. So that's you know, another mechanism that they could do. There's another implication, of course, of autonomous vehicles writ large, which I see in terms of this whole space, is that it's going to change the need for parking. And my hope, and again, this is really maybe just my naivete, and my hope, is that that will actually create space to re-architect the urban transport system so that they're actually can re-architect to make the bikes and the scooters be safer and have a space to ride in a more protected way. Whether that can happen, that may be my pipe dream. But I think that certainly is, I mean, there's no question that there's a linkage between greater autonomous vehicle use and a decrease in the need for parking, but exactly how you can do that in terms of increasing the capacity of the roadways, and whether you want to use that capacity of the roadways for traffic, which actually, of course, probably will be a consequence that will, you know, autonomous vehicles may, I mean, just as the existence of Uber and Lyft have caused major congestion problems in the cities, then there's the question of what that will do overall. And so there'll be trade-offs in a variety of ways, which will cause us to re-architect. But of course, this is all one piece of the layer, you know, that you talked about earlier in terms of the questions of you know, connected car networks and the ability to engineer better ways of routing and centralized control for vehicles overall. There are security issues, but there's a question of, you know, like Hamza talked about, we think the capacity of our road network is given, but with the right better control, all of a sudden that may change dramatically. And certainly centralized control by, you know, Internet of Things kinds of approaches is going to change the landscape. So, you know, it's one important layer, but I mean, speculating in this thing, you know, it's the old adage, you know, prediction is hard, especially about the future.
Sorry.
Add to that, there's a parallel to be made with air transportation. So in the late 1990s, we already had pilot programs on highways of, you know, fully autonomous vehicles and platoons, like Saurabh was saying. And so in terms of doing that in isolation in very protected, specific areas of infrastructure, I think the technology was there decades ago. But we've still now, you know, decades later, still confronted with the fact of what happens if these autonomous vehicles are really, you know, fully automated, autonomous, in urban environments where there's a lot more uncertainty and where they're not as protected. And I think there's I think, a long way to go before we can actually do that. I mean, Waymo just got, a couple weeks ago, permission to do that in California without any driver behind the wheel. And so, you know, there's a hype saying, you know, we're going to get soon to be able to do that. But I think if you ask most traditional transportation folks, they would say there's a long way to go before we actually see that. We'll see increasing levels of automation, just like we have seen in air transportation, but, you know, full automation, full autonomous, this dream of I'm going to be reviewing papers while I'm going to work and my car will drive itself. I think we're a long way to go before we actually see that.
So I just wanted to kind of make two brief points. I think with regard to the way in which the autonomous traffic is going to interact with the regular traffic, whether it is segmented priority or mixed traffic, I don't think really we have any understanding of how our infrastructure is going to behave, right? So I fundamentally think that there is a need to kind of have new modeling and analysis techniques to really understand how fundamentally the nature of the supply side, the infrastructure side, is going to change in the presence of this mixed autonomy systems. And the second is with regard to the security questions. In terms of the analysis of the security questions, it is the interplay between strategic aspects and the way in which the physical system responds, right? So this actually raises new questions about how to model this kind of strategic behavior. And what does it mean in reality in terms of the impact of the resulting strategic models for policy, for example, for insurance industry, for diversifying risks. And this kind of interplay between the impact of these malicious actions or unintended actions on the incidents and how to kind of control the risk related to these incidents, there's something which fundamentally also needs to be investigated.
Yeah.
I have sort of a long, rambling, two-part question. Really interested in what you presented regarding the airlines, and that's interesting what you mentioned about, in general, cities not being able to either build new airports or expand their airports. And that does seem like a perennial question, because we see like the air traffic numbers going up. But what do you think is really like the solution? And I mean, I remember like 15 years ago, we were having the debate of what was going to win out, either like the Airbus, the 350, the double-decker huge plane, or the 787 Dreamliner. And in the case of Airbus, it was like a large batch movement of passengers, which favored like a hub and spoke system, whereas the 787, like a smaller, more flexible plane that favored like point-to-point direct flights. It seems to me like maybe like in a from the standpoint of increasing traffic, maybe like the large plane batch movement would be better, but it seems like commercially maybe like the 787 model went out. And also, I don't know if any of you studied the Mexico City airport. It's like the biggest story. I'm from Mexico. It's like the biggest story in Mexico for the past month, even though it hardly got any news coverage here. But Mexico was planning on building. Well, actually, it's like 35% completed. I think like the third largest airport in the world. And the president-elect decided to cancel the airport, and he claims he can recondition the current airport, plus add a satellite airport and reach the traffic goals. And he claims to do this in 3 years. Is this fantasy? And has this been studied? And if not, I think it'd be like a great thesis topic for one of your students. I told you it was a long, rambling question. Sorry.
You want to start?
Okay. So I think the part of the thing when we think about what aircraft and issues like that is there are trade-offs here. And I think we haven't done a good job of articulating and identifying trade-offs and interdependencies. So we'll start with the first thing on why is it hard to build an airport. I think the reason for building new airports in places like in the US certainly has been a range. One is there isn't very much real estate. I mean, we're out of space, right? So busy urban areas, you can't build, you don't have room to build a new airport. There are certainly environmental issues now. So, the process that it takes to build and the capital that you need to build a new airport is huge. And I think, the reason I put up the quote from 1979 is I think the argument that the only way to meet demand is through building a new infrastructure is a hard one to make because we seem to manage fine.
Maybe I could just interject in that. We did this study once where we were looking at exactly this issue and trying to understand the scheduling practices that were leading to congestion. And there's a lot of things going on that can be addressed without increasing airport size. So for example, if you got rid of competition, which you don't want to, but if you did, you would find that you could service with the same frequencies and quality of service, all the passengers, and reduce delays. Essentially, you can wipe them out. Okay? So what's happening with competition is that airlines are competing on schedule, and this is exacerbated in the US by the fact that our policies allow airlines to schedule lots of flights into airports, and our structure of taxes, for example, are kind of flipped from what they should be. So, you know, having a fee structure that is based on the wear and tear on the runway surface, resulting in higher fees for larger planes, is really the opposite of what you want, because it takes about the same amount of time to have a large plane as a small plane land, and the scarce resource is that runway. There are many things you can do to, both through policy and sort of administrative controls, operations, where you can realize more capacity in your system.
To piggyback on a couple of things that Cindy mentioned, I think the issue also is that, you know, it's what you care about from the system perspective and what the airlines care about, right? So Cindy talked about them competing on frequency. So I think pretty much all empirical evidence suggests that delay alone does not lead to aircraft, you know, airlines deciding to reduce their frequency and have larger aircraft. That they would, given that choice, they would eat the delay, but, you know.
Although in the last 10 years, we've seen airlines change that practice.
It has to, there's a fair amount that they'll go before it gets to a point where they're willing to do that. The second thing with really large aircraft like, you know, the A380. So one thing is, it's not just that it's a runway resources. You need to have bigger gates. You need to have bigger taxiways. So there's everything in the layout that you now need to increase. And so the question is the cost of that worth being able to serve, you know, the extra aircraft? And I think it varies, right?
I think your example about the Mexico City new plan is actually a really fascinating question, and it relates to what we were talking about earlier. I think that one of the things that we have to think about is, as you have those new designs, you have to think about passenger behavior and choice. You know, as you make moving around a city with Uber and scooters and bikes more convenient, you stimulate demand and you see people behaving in different ways. And I think that part of what would be fascinating for OR people is to work on building the models that capture those changes in behaviors. And do we in fact have congestion because vehicles, autonomous vehicles or not, are waiting for their next pickup? You know, how do the needs of the system and affect how the design of that system should change? It'd be great if we could use our models to provide that sort of information to decision makers.
Yeah, this is a good point. So essentially, not forgetting the demand aspect of all of that, right? So essentially, when you realize why Uber and Lyft became so successful is because most of the taxi operations were lousy, and we like to travel, and you know. So why do we have congestions on the airport? Because we like to travel. We like to go to Thanksgiving. So it's our problems, right? So, so my question, last one perhaps, is do you see an options for the air transportation not too far in the future where there will be disruptors that basically say the system is really not efficient the way it is, and we're going to provide something that customers like us will use? Or is it too different?
No, I think it'll happen. So, and I think there's a lot of what Carolina talked about, where in the air now, when you think about the groups that are moving in and are interested in it, they're not traditional airlines, right? So nobody is talking about starting a new airline in the U.S. markets. It's basically having, you know, on-demand mobility. right?
So
Or
I'm aware
package
of
deliveries.
recent PhD students from MIT, not necessarily from the ORC, but are currently working in Silicon Valley with companies that indeed develop these planes that take off like that, right? And
So they're mostly VTOLs.
operate in an urban environment.
So they're mostly going to be, exactly, very short urban air trips, so urban air mobility. And in the very short term, they'll be piloted. But I think the view is that, there's like pilot shortages, right? So I'm guessing that if the price of drivers ends up being the large, part of the cost of operation of car companies, they'll move to autonomy. And I think it's the same thing where if the demand picks up and there's actually a market for it.
So who owns the space just above the urban, not the very high altitude, but just above a building? Who owns that space?
I say you own up to 400 feet.
So everyone can have access to it, or do you have to file a license to?
So very low. I mean, if you have a hobby drone right now, you can fly. I think there's a little bit, in terms of the registration on very low altitude you can do, but anything that's higher than that, the FAA owns. And you can't do, and you don't own airspace that's close enough. So MIT is close enough to the airport that you actually are restricted.
All right, are there last question? So let's stop. This is the end of the 65th anniversary. I would like to thanks again the last panel. The speakers, and the